Hi, everybody. Just thought I would give you a brief rundown on error correcting codes. One of the codes that I think is perhaps the most common is called the 7-4 Hamming code. Seven four Hamming code is a code that has 7 code word bits. The number of bits that you would have in a message is equal to 4 bits, and the number of bits that you have for the check, this is check bits, okay, is equal to 3 bits. So what we see is that there are a certain number of bits, 3 bits, allocated for overhead in the code word. And that code word gives you a certain amount of, we'll call it redundancy, R, which is equal to the total number of bits in the code word divided by the total number of bits in the message, which in our case is going to be something on the order of 7 divided by 4. The basic idea of redundancy is you are able to either correct codes or check for error. In a case where we have 3 check bits, we can do single error correction, or double error detection. So with this idea in mind, what we can see quickly is that n is equal to the number of message bits, m, plus the number of check bits, k. And that's an easy formula to see, basic arithmetic. And what we want to do is we want to formulate what's called a P matrix. And the P matrix is also known as a submatrix. And a submatrix is a matrix within a matrix. And so what we do is we use something called Hamming's rule. And Hamming's rule says we'll let m rows, where m is the number of message bits, all have k, which equals 3 bit words. So now we've got 7 rows by 3 bits worth of column. Let the m rows have all 2 or more ones in any order. So what we'll do is we'll just set up 1 0 1, 1 1 1, 1 1 0, and 0 1 1. So what we have here is the submatrix, which is called the P matrix for parity. And what it has is 1 2 3 4 rows total, m rows. I said 7, but that would be n. M rows, and they all have 1 2 3 bit words, and all rows have 2 or more columns in any order. Hamming's rule. We also want to set up a identity matrix. And the identity matrix is going to have exactly m columns, and it's going to have exactly m rows. So it's an m by M matrix. So let's take a look at this identity matrix. We'll call it I sub M. And we will set it equal to something that has its identity matrix. So what we have here is an M by M identity matrix, I sub M. So this is called a 4 by 4 identity matrix for the 7, 4 Hamming code. So now we've set up a couple of matrices. We've got a P matrix, our parity matrix, and that's a submatrix. We've got our I sub M, our identity matrix. And what we want to do is we want to create a new matrix which consists of H sub T. And that's going to be equal to the parity matrix over a I sub K matrix. An I sub K matrix is going to be a matrix which is going to be K by K, or 3 by 3, in an identity. So an I sub K matrix, I've got another matrix, it's going to be 3 by 3. And now we have a way in which to formulate our new H transpose matrix. We take our P matrix from here, and we write it up here. We take our identity matrix and write it underneath. And now you can see why we call P the submatrix. Because here's your P matrix, and here's your K by K identity matrix. And what you want to do is you want to take a code word, code vector, X, multiply it by H transpose, and have it equal 0. And that's what's going to happen if there are no errors. Now let's go back to our little M by M identity matrix. We're going to create what's called the generator. The generator is equal to I sub M along with P. And we can write that out. Take your I sub M from here and your P from over in here, and you create your new generator. Now we go to the P matrix. And now we observe there's 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6, 7. So this is a 4 by 7 matrix. 4 is the number of message bits. 7 is the number of code bits. So that is an M by N matrix. the generator is equal to an n by m by n generator matrix for the nm Hamming code. So we've got the block of message bits, C, which is a block of check bits, and X, which is a code vector, which is going to be created such that we have message bits and check bits in a single vector. So now the question is, how do you get a code vector? And so what you want to do is you take your message bits make them into a sub-vector, add your generator, and then you're going to have your code word. So how do I get my code vector? I generate it. This is my check bits, sorry, check bits. I generate it using x equal m times the generator. So now I've got my generator, where the generator is equal to the identity matrix, which is going to be 4 by 4. That's an m by m matrix. And I'm going to have my parity matrix. So there's my generator. I'll multiply it by my message, and I'll get a code word. I'll obtain my check vector, C, because I need both the code word and I would like a check vector. So I get my check vector by taking m and multiplying it by the parity matrix. And so that's going to be a 1 by 4 times a 4 by 3, and that's going to equal a 1 by 3 using basic matrix multiplication. So now let's take a look at various messages and various check vectors that we can obtain here. So here's m, and what we'll do is we'll create a series of messages. And for each one of these messages, we'll use a check vector. So let's see if we can identify the so-called weight involved in each one of these by counting the total number of bits. So there's going to be 3 bits here, 3 bits here. Looks like there's 4 bits here, 4 bits here, 4 bits here. Nope, that's 3. That'll be 3 bits, and this will be 4. So now we've got messages and check bits. So we'll get a transmitted code word X, and we're going to get a received code word Y. And it turns out that if you've got an error, X does not equal Y. Now, if X is not equal to Y, we know that's an error. But if X equals Y, it could be that we still had an error. There's a non-zero probability that there will be an error that we did not detect. And so what we want to do is we want to make it so that Y is equal to the error exclusive OR, this is a bitwise exclusive OR, with X. And so X must be equal to Y with a bitwise exclusive OR times the error. And the error is going to flip a bit. And what we're going to do is we're going to make it so that we're able to obtain the location of the error by solving for the error using our generator polynomial. I'd like to take a few moments and take a little aside about syndromes. Syndromes allow us to point to error. Now, one thing we can say about the syndrome is it's a 3-bit quantity which is extracted from a simple multiplication. We take the X vector, do a mod addition with some error which perturbs one of the bits, multiply it by H transpose, and if you recall, H transpose is equal to a P matrix composited with a K by K identity matrix. So now we look at this and we say, well, I can multiply that matrix out, and I can say that this is X times H transpose plus some error times H transpose, just cross multiplying. And one thing I notice is that X times H transpose should be equal to 0. That gives me a simplification that says that the syndrome must be equal to the error vector times H transpose. Let's take a look at what some potential error vectors will be. What we'll do is, this is it for the 7-4 Hamming code. And in the 7-4 Hamming code, we have 7 bits. And so errors can occur in any one of the bits. So we could have 1, 2, 3, 4, 5, 6, 7 bits with no errors. And on the left, we'll put in a syndrome. And on the right, what I'd like to do, just for convenience, is put H transpose, where H transpose is equal to P adjoined with the K by K. And so we'll write that out for convenience. Here comes the P matrix. This is going to be a 7 by 3. So there's 3 columns. There'll be 7 bits total. So there's your P matrix. And now we're going to put in the K by K identity matrix. Here's the K by K. And this is a 7 by 3. And so what we're doing is we're taking this error vector, which is 1, 2, 3, 4, 5, 6, 7, a 1 by 7, and we're multiplying it by a 7 by 3. So this is a 1 by 7 times a 7 by 3. And that's going to give us the 1 by 3 that we need for the syndrome. Take 0, multiply it by this, and you get 0. Do the next row, you get 0. Next row, you get 0. And that's a syndrome. Let's do it again. We'll put a bit error, 1 bit error, right in here. So that says a bit will be flipped in the most significant location. And that'll be 1 times all of this, that's going to give us a 1. 1 times all of that, that's going to give us a 0. And a 1 times the other is going to be a 1. And that's a syndrome. Let's do it again. And now we have 0. We got a 1 in the next column. And then we have 0. Let's see, no, it's going to be a 1. And so now we have 0, 1, 1. Let's do it again. And now we have the third row. That's going to be 1, 1, and 0. And similarly, one, 2, 3, 4, 1, 2, 3, 4. So that's going to be 0, 1, 1. And we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's going to be 1, 0, 0. And that's going to be 0, 1, 0. And that's going to be 0, 0, 1. And that gives us a syndrome. Now let's take a look at how we're going to use this syndrome to do an error correction. Let's assume that we want y times h transpose, and we get a number out. And we want to multiply it by, this is what we've received, h transpose, which is down here. And then we put in our K by K identity matrix. So there's the K by K. And now what we can do is we can multiply this by that. 0 times 1 is equal to 0. 1 times 1 is equal to 1. 0 times 0 is equal to 0. 1 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 0 is 1. So this is equal to 1. And that is going to be check bit number 1. We'll do the same thing for the next column. 0 times 0 is 0. 1, 0. There's another 1. 1 plus 1 is equal to 0, because we're dealing with mod 2 arithmetic. 0 times 0 is 0. 1 times 1 is 1. So at the end of the day, check bit 2 is equal to 1. Do it again. 0 times 1 is 0. 1 times 1 is 1. 0 times whatever is 0. 1 times 1 is equal to 1, so 1 plus 1 is equal to 0. So now we have 0 times 0, 1 times 0, and 0 times 1. So now check bit number 3 is equal to 0. So now we have the check bits being equal to 1, 1, 0. That's our syndrome. We take a look over in here for 1, 1, 0, which is right down in there. And we see there's an error in this third bit. So we take the y, mod to it with the error in order to flip the bit back. And so that is now 0, 1, 0, 1, 0, 1, 0 with the error vector 0, 0, 1, 0, 0, 0, 0. And what do we get? 0, 1, 1, 1, 0, 1, 0. And that should be the original transmitted code word. Right down there. So we use the syndrome to determine which bit has been flipped. And then we use that information about which bit has been flipped, which bit has been flipped in error, and we flip the bit back and get the original code word. And that is the essence of the application for Hamming codes.